Good evening, everybody, and welcome to tonight's webinar, which is on selectivity of protective devices. My name is Paul Chaffers. I'm the Technical Events Manager at NAPIT. And joining me on this webinar is Richard Townsend, our Technical Editor. And we've got some special guests from Hager, Paul Collins, who's Technical Manager, and Ian Wassell, their Trainer Manager. So those guys are going to jump in and give us a bit of detail at the relevant points. So straight away, I'm sure you're all familiar with what selectivity is, but for the guys that are still using older terminology, it was previously known as discrimination. And basically, it's the ability of a protective device to operate in preference to another device, which is in series. So it all sounds fairly simple, really, but let's have a little look at the definition. So there's a little picture there, which we've got in the BS 7671 figure 536.1. And what that's showing there is if we've got a fault on overcurrent protective device 21, we're not going to take out overcurrent protective device 1 because that's feeding device 22 as well. So that's basically what the principle is. And we're going to see some more images of this shortly. This is the definition, and it's a big long-winded thing. It talks about the coordination of the operating characteristics of two or more protective devices such that on the incidence of overcurrent or residual current within stated limits, the device intended to operate within these limits does, and the others do not. Okay, so it's talking about two types of characteristics, overcurrent and residual current, and we're going to mop all that up in this webinar tonight. Now, there is a sort of further note to the definition, which basically talks about the ability to achieve selectivity on the devices when in series, and it introduces partial selectivity, which is selectivity up to a given overcurrent lower than the breaking capacity of the downstream device, and it introduces total selectivity for all overcurrents up to the value of the breaking capacity of the downstream device. So there's quite a lot to take on board there. So let's have a little look at this image here. This is all of our loads and they're all energized. Now, if we introduce a fault on this circuit here on the bottom right hand side there, we've got actually 4 protective devices in series. Okay. Now, obviously, to achieve selectivity, we only want D to operate and we want the other 3 to remain energized. Otherwise, we would lose loads throughout the installation that was not the intention. So there we have it. In this instance, only that one protective device is operated and therefore we've achieved selectivity. So that's what it's all about. Now, the big question is, quite often asked, and all of the guys that are on this call tonight, we've all been asked it over the years, and I certainly know I have on a number of NAPIT forums and panels that I've sat on, is selectivity mandatory? So i.e., do we have to do it? And the answer is no. It's regulation 5364121 states that where selectivity is required, okay, and then it gives us some things we have to do, but let's just leave it on that a minute, where selectivity is required. So as the designer, you would need to ask yourself, is it required? So if you are designing a complex installation, maybe a school, a data center, or a hotel, could be a hospital, then quite often there's going to be aspects of that installation where you're going to want to achieve selectivity because of the interruption that will be caused if we do not achieve selectivity. Okay, so in that case it is required. But if you were working in a domestic setting and you were doing a installation in a garden shed and there was no real desire to achieve selectivity, then we wouldn't be so concerned. Of course, it's always a conversation with the client because the client may want to achieve selectivity, and that would be for a high-end installation. Maybe they have a gardener come round and look at the property and deal with the outbuildings in the garden, and you wouldn't want anything tripping in the house because the homeowner often goes away on holiday, so that would be where you would want to achieve it. So it really is down on a case-by-case basis, and we quite often see people say, oh, I've got to put a switch fuse in for the consumer unit, which is remote from the intake position. How do I get selectivity between the service intake fuse and the switch fuse. And to be quite truthful, you need to ask yourself, is it really required? Because to achieve selectivity there, you would have to, you know, seriously reduce the size of the overcurrent protective device to achieve that. And I'm going to stop that there because Paul Collins from Hager is going to show us some examples of this later on. Okay, so where we do want to achieve selectivity, the regulation gives us some bullet points. It talks about desktop study. Okay, so you've got to take into account the relevant product standards and manufacturers' literature. It gives us the option to use appropriate software. Okay, but the information still has to come from a manufacturer. Test in accordance with applicable product standards. Okay, so you would need to obtain that stuff, or a manufacturer's declaration. Okay, so these are the things we need to do if we want to achieve selectivity, and my colleagues are going to talk you through that shortly. But one other aspect to look at is this regulation here, which talks about coordination requirements. And when selecting electrical devices, the interaction between those devices shall be considered so that it do not adversely affect the safety of the installation. So going back to the simple question, is it mandatory? Do we have to do it or not? It comes down to, are you going to affect safety if you haven't achieved selectivity, and what type of installation is, if it's desirable or not. So hopefully that's cleared up that myth there. Now, when we talk about coordination of electrical devices, we need to consider short circuits, overloads, and residual currents. And the aspects for coordination of those devices would be that we looked at selectivity, we looked at short circuit protection, and also overload protection. Okay, so at this point, I'm going to hand over to Ian from Hager, who's going to talk you through selectivity by time current. Over to you, Ian.
Good evening, everybody. Right, we're going to have a look at the time current characteristics for devices. And by using these time current characteristics, we can help us gain selectivity from devices. So first of all, we're going to have a look at the graph we've got in front of us now. So we've got device number 1 is the one that's highlighted in red, which is a BS882 fuse. Okay, that's 100 amp. So that would clearly be our supply fuse. Now, next to that, we're going to install a 63 amp MCB type C. Now you can see when we get to the bottom of the curve there, before it goes on to its magnetic factor, it slightly overlaps onto the fuse. Now the problem there is above 500 amps, we could actually get or lose our selectivity. Okay, so what can we do to prevent that happening? How can we keep our selectivity? So if we move on to the next slide, one of the things we could do, we could change the MCB. So instead of having a type C MCB, we could go on to a type B. And you can see there the curve for the type B MCB is slightly different. Okay, so we don't actually overlap into the BS88 fuse anymore. So in that case, we actually gain our selectivity. Now, one of the things to bear in mind there is, how's that circuit been designed? Okay, now if the circuit has been designed specifically with a type C fuse or MCB, sorry, we would have to have a look whether changing that for a type B would in effect alter the design of that circuit. So that's something we've got to sort of remember. Now, if that is a problem and we need to use a type C MCB, there is another way we can look at it. Okay, so in this next slide here with the graph, what we've done this time is we've changed the BS88 type 2 fuse from a 100 amp fuse to a 125 amp fuse. That has then moved the curve of that fuse away from the MCB. Now again, there are design criteria involved in this, so we would need to look closely at design of this installation to say, okay, can we use a 125 amp fuse instead of a 100 amp fuse? And also we need to take into consideration any wiring downstream of this device would need to be able to cope with the bigger load that is available to it. Okay, if we move on to the next slide. Now, if we can't do either of these two things, the next thing we could do, we could look at replacing that BS88 type 2 fuse with an MCCB that's adjustable. Now, there's all sorts of adjustable MCCBs on the market. We can have adjustable for current and adjustable for magnetic. Okay, now we can get a totally adjustable device, which we can adjust both sets of on the curve there. So first of all, we'll take a look at this. So we've got 100 amp MCCB device in there, and it overlaps on the magnetic side. Okay, so it's overlapping the MCB. Now, if we have a look at the settings for that MCCB, we can see that IM is set to 6.5. Okay, so that's an adjustment we can make. So if we make that adjustment to 10, okay, we move that up a notch. Okay, and we can see that what we've done is we've moved the magnetic factor of that MCCB away from the MCB. Again, there is things that we need to take into consideration with the design of the circuits, the design of the installation. But with these adjustable devices, it allows us to maintain selectivity again if we need to do that. Okay. Now I'm going to hand you across to Paul now, because Paul's going to discuss with you energy-based selectivity. So where we get faults over 2 to Ka, okay, it's Paul's going to explain these ones to you. Thank you, Paul.
Thanks, Ian, and so good evening, everybody, from me. So what Ian's been talking about up until now is relatively low levels of fault current. So when we can look at the actual time current characteristics of the two devices in series to make sure that the downstream one will operate before the upstream device, and therefore achieving your selectivity. Now, all of these curves, you'll notice that kind of run out basically when we're talking about very fast disconnection times. So when we're talking about instantaneous tripping, which is pretty much 0.1 second or less, you'll notice the fuse characteristics even stops there. Now, clearly, of course, that can't happen in the real world. It must carry on and trip less than 0.1 of a second if we increase the current through the fuse. So what we need to consider when we're up at the higher levels of fault current is actually looking at the energy-based selectivity rather than time current characteristics. So this is what I'm going to do now, and it's first of all I'm going to lead on to what sort of desktop studies for energy-based selectivity, and then we look at the kind of the easy way that you could probably get data from manufacturers to decide whether the two devices you are considering will provide you selectivity, be it partial selectivity or total selectivity. Now I'm going to consider upstream devices and downstream devices, and looking at fuses and circuit breakers. Now the circuit breaker could be an MCCB or an MCCB. It really matters not. They're essentially both the same device. An MCCB and an MCB is the thermal magnetic devices. Now I'm going to be talking about the tripping characteristics of these devices at the higher levels of fault current. So I'll be talking about the magnetic characteristics of the circuit breakers, not necessarily the thermal part of the circuit breakers. So there are 4 possible combinations of protected devices, upstream or downstream. We could have fuse upstream, fuse downstream. We could have fuse upstream, circuit breaker downstream. Uncommonly, we could have circuit breakers upstream and fuses downstream, or circuit breaker, of course. Now, we need to know what causes the devices to actually trip. Now, if we take the first example there, we've got an upstream fuse. Now, what operates a fuse is energy, basically heat energy. And heat energy in terms of electrical fault characteristics is given to us by the I²T value. Now, those of you who are used to the adiabatic formula would recognize the I²T. It's part of that formula, part of the energy that is deliverable down to, for cable sizing, we may usually use that I²T and divide it by a K factor. but the I²T is actually electrical energy passing through a device. So first of all, the top line then, if we've got a fuse upstream, fuse downstream, okay, the downstream device, if it sees a fault, will have a total let through amount of energy given to us by probably the manufacturer in terms of a complete clearing I²T, or total let through I²T. Now, because the upstream device is a fuse, we need to know the I²T value. So that's what I mean by the downstream device determines the value. So the downstream device is telling us we need to understand what the I²T is that will go through the downstream device. Now, the upstream device determines the method. The upstream device, being a fuse, will have a pre-arc value. Now, the pre-arc value of a fuse, you probably know, is the value of energy that can go through a fuse, allow it to be stressed up to a point where it will recover. If it sees more energy than the pre-arc value of the fuse, once it's gone past that value, it cannot recover. It will go all the way and actually disconnect as well. So that's the kind of the important point of the first scenario there. The downstream fuse must not let through more energy than the pre-arc value of the upstream fuse. And I'm going to look at this as I'm going to give some examples with numbers in this shortly, and also we're going to look at circuit breakers as well. So if you could advance the slide, Paul, if you don't mind. So what do we have here as an example? So saying we've got the fuse, upstream, downstream. Now in the blue fuse, this is just some data from fuse manufacturers, is a 63 amp LET part of it. Is just part of their part number. Not sure what that means, to be honest with you. It's probably just how the tags bolt on or connect in. So the 63 amp fuse, if you can see the data from the fuse manufacturer, what I've highlighted in blue there, would clear at 240 volts, 2,200. Now 2,200 watt. If you look at the units on the top of that table, 2,200 amp squared seconds, I²T basically. So 2,200 packets of heat energy, we could consider that as a scenario as. Now the 100 amp in yellow upstream fuse, you can see from this manufacturer's data, has a pre-arc value of 600 amp squared seconds. Now what that's telling us is if the downstream fuse lets through more than 600 amp squared seconds, it cannot recover. It's going to go beyond its pre-arc value. That will operate as well. Now 2,200 is clearly more than 600. So you see these two fuse combinations, okay, will clearly not provide selectivity. Okay, this just won't happen. So which fuse downstream from a 100 amp upstream fuse could provide selectivity? Hopefully you might see there it's the 35, 32, 25 or less type of rated fuses. So we've got to have the clearing value less 600 or less. So a 32 amp fuse could provide total selectivity to a 100 amp supply fuse. And as Paul said at the start of this seminar, really, if you try to have a 100 amp supply fuse and you try to have a switch fuse after that, because they're consuming it's in a remote location, it'd be very, very difficult to provide selectivity between the 100 amp supply fuse and a fuse in that switch fuse. But do we need to? Okay, is the question there. Next scenario, if you wouldn't mind, Paul. So the next scenario we've got is the fuse upstream. And I've kept the same fuse for this example, but this time we've got a circuit breaker downstream. Now it's more or less the same thing we have to consider. So we have the fuse upstream being 100 amp, has a pre-arc value of 600. Now how much energy would go through a 63 amp circuit breaker under fault conditions if it was the downstream device? Now, these are the lesser known tables you'll see from manufacturers, but you should be able to get these from most, if not all, manufacturers. This is the graph, if you can see on the left-hand side, of the let-through energy on the y-axis versus the amount of current, so versus the kind of the fault current. It's a weird shape, this graph, because it starts off how the in thermal operation, if you like, and then there's always a vertical line when the magnetic part of the circuit breaker takes over, and then there's kind of more or less a straight line that goes kind of diagonally upwards and right. Because with circuit breakers, the actual energy let through is proportional to the current. It's because it's I squared T, it's not a certain value. So as the fault current goes up, the actual energy that can pass through or will be allowed to pass through the circuit breaker as it clears that fault actually goes up as well. So in this example, I've said that, okay, let's say there's a 1000 amp fault after the 63 amp circuit breaker. So you can see the red line trailing up, and it's difficult to read because these lines are very close together. So where do we cross the line of the 63 amp circuit breaker? Hopefully you can just see roughly where that is, and then read to the left, and it's comes out at the value of about 3.5. But just be careful of the units. Sometimes manufacturers use just amp squared seconds, and sometimes they use K or 1000 amp squared seconds. You can see the unit here is K amp squared seconds. So in a desktop study, the circuit breaker will let through 3,500 amp squared seconds to clear a fault of 1000 amps. Is that going to provide selectivity with the 100 amp upstream fuse? Clearly not, because it's more than 600 amp squared seconds. So the desktop study again doesn't provide us with adequate values and information to prove selectivity. Next slide, if you wouldn't mind, please, Paul. Now, desktop studies don't give us the best information, actually. They are very theoretical, of course, desktop studies. If that's the only information you have, however, then that's the only information you can use. But what you should find from most manufacturers is they will provide you tables of selectivity, which are based on repeated tested information. So, for example, this table is a table from one of our brochures that tells you some selectivity information between an upstream BS88 fuses of certain different ratings, obviously from 10 amps all the way to 100. And on the side there, you can see it's related to B curve circuit breakers, 6 amp to 63 amp. Now, in the yellow, we've got the 100 amp fuse, you can see in the graph. And if you cross-reference that on the kind of left-hand side to the 63 amp MCB, you'll see a value of 5.3 in that box. Now, what this means is, in the real world, okay, we can achieve partial selectivity if you had a 100 amp BS88 fuse upstream of a 63 amp type B circuit breaker up to a fault value of 5.3 Ka. So if the fault is where the MCB is installed is 5.3 Ka or less, you will achieve selectivity. If the fault where the 63 amp circuit breaker is more than 5.3 Ka, you won't achieve selectivity if your fault is at that kind of value over 5.3 Ka. Now, you'll also see T's in some of these boxes. T provides total selectivity. Okay, so regardless of the value of the fault, up until the breaking capacity of the downstream device, you will achieve selectivity. So, for example, if the downstream device was a 50 amp circuit breaker, you will achieve selectivity all the way up to the breaking capacity of this particular downstream MCB, which is actually a 6 Ka circuit breaker. Now, the next example is circuit breaker upstream and circuit breakers downstream. It gets a little bit more complicated here, especially when we're talking about, again, desktop studies. And if you're talking about different manufacturers, you may have to use desktop studies, but you won't get the best information because it's not information based on the kind of real world scenarios from testing. So what I'm going to show here is a 200 amp MCCB that's upstream of the same 63 amp MCB. Now, and the time current curve shown there is the response curve in terms of time current of the 200 amp MCCB. So as I said earlier, when we're talking about high levels of fault current, it's not thermal part that's going to be tripping this circuit breaker, it's magnetic. So what the magnetic what activates the magnetic part of the MCCBs, or MCBs of course, is on the magnetic part of the device, is the instantaneous value of current at any one particular time. So we can have a method of calculating the minimum peak tripping current of a 200 amp MCCB, and it's given in the formula shown there. So if I can hopefully take through this slowly, and hopefully it will make some sense. So 200 is the rating of the circuit breaker. Now, a lot of these MCCBs, as Ian told us a little while ago, have adjustable magnetics. So if you adjust the magnetic, of course, you're adjusting the tripping characteristics of the magnetic part of the circuit breaker. So let's use, for this example, the magnetic setting is on 10. So 200 times 10 is the magnetic setting, is 2000, of course. 2000 amps is going to operate the magnetic part of this circuit breaker. Now, when you show time current characteristics as is shown here, you have to be very careful, because the magnetic tolerance, or the magnetic hazard tolerance, and it actually is quite large. The magnetic tolerance is plus or minus 20. And it depends what we're using this for, or what we're trying to calculate, whether we're going to plus 20% or minus 20%. If we was using this to calculate earth fault loop impedance, for example, we need to know the most current that will operate this device. So we actually add 20% to this value. If we want to work out what will avoid its unintentional operation, which is what our consideration now, we have to minus 20%. So 2000 minus 20% magnetic tolerance is actually down to now 1600 amps. 1600 amp RMS will operate this 200 amp MCCB. Now, we don't need RMS, we need instantaneous values. So we also need a multiplication factor of square root of 2, which is the 1.414. So after all that tells us that the 200 amp MCC would trigger or operate if it saw an instantaneous current value of 2262 amps. Now, we need to remember this value, and we need to compare it with some information, again, give us from the manufacturer of the downstream device. And it's a similar chart to give, or table given to us as before. So this is the another lesser well-known piece of information given by circuit breaker manufacturers. You can see it's similar to before, but not quite the same. This is a graph that represents the peak cutoff current versus fault current of different ratings of circuit breakers. And as an example here in the red, I've said, okay, for example, let's say there's a 3000 amp fault. So we look at 3000 amps on the x-axis on the bottom, trace up till you see your particular circuit breaker. And again, I know they are quite difficult to follow, so you can only get really an approximation. So follow up till you see where you clash with or cross with a 63 amp circuit breaker. Read left, and you can see it's at the value of 3. Again, just be careful. Sometimes the units are amps, sometimes they're Ka. You can see the units here is in Ka. So what this tells us is that the 63 amp circuit breaker at a fault of 3000 amps would disconnect and clip the peak of the current, if you like, to 3000 amps. Now, because it's a 3000 amp fault, 3000 amp cutoff value, that's purely coincidental. So if you see the 10,000 amps, you see that doesn't relate to 10,000 amps. So, okay, don't relate the fault value to the peak current cutoff value. You do need to trace it from the curves. Now, so the downstream device, 63 amp circuit breaker, okay, will disconnect when the peak current value reaches 3 Ka. Is that more than 2,262 amps for the upstream MCCB? Yes, it is again. So using the desktop study, in theory, then it does not provide selectivity. So again, another reason why desktop studies don't really give us the most accurate information that we would like to see, but sometimes that's all we have. If we had different manufacturers, one upstream, one downstream, we may have to use desktop studies. Again, this is another table given in our brochure. Of course, other manufacturers should give similar information. They will have different numbers, of course, in their tables, but this should provide the similar information. So you can see this is a selectivity table where the upstream device is MCCBs, and anyone used to our range of MCCBs, we have X160, X250, H250, etc. So this would have been a 200 amp X250 upstream device. Cross-reference that with the 63 amp MCB that's on the downstream or on the left-hand axis, and you'll see a T in that box. So again, total selectivity would be achieved in the real world between a 200 amp MCCB and a 63 amp MCB downstream from it. So where there's T's in these boxes, total selectivity is achieved. Remember, if there's a number in these boxes, you will achieve partial selectivity up to the fault value given to us in that box. Now, because these are tested results, okay, you tend to only get the same manufacturer upstream, downstream. You can imagine how many combinations it would be for all the manufacturers to test all their devices with someone else's manufacturer upstream, someone else's manufactured device downstream. So you'd only get these kind of tables from tested values where the upstream and downstream device is of the same manufacturer. Now, in a practical example, okay, so how could we use this in a practical example? So on the right hand side of this slide there, what I'm trying to show there, maybe we have an MCCB panel board. It could be part of a house, of course. It could be in a school. It could be an office or whatever. So in that MCCB panel board, there's a 100 amp MCCB, and it's feeding some single phase sub distribution boards, or final distribution boards, sorry, from that 100 amp. So our upstream downstream device we have to check for selectivity is the 100 amp MCCB upstream and the devices in the downstream distribution board. Now you can see in the downstream distribution boards we've got different combinations of devices. In practice, we don't have to check them all. What we do is check the highest one or the largest one. So what we need to check is 100 amp upstream MCCB, 32 amp MCB downstream, and if we achieve selectivity between those two, of course we will also achieve selectivity between 100 amp upstream and a 16 amp downstream or 6 amp downstream. So just pick the highest one or choose the highest one, and we also need to choose where the fault current of the circuit of the downstream distribution boards is the greatest. So I'm showing two distribution boards in this picture. We can see the fault current at the first distribution board is 8 kA. Now, of course, it's quite handy that we have to actually ascertain what the prospective fault current values are at all relevant points, which are at distribution boards. So we will actually have a measured value of what the fault value is at that first downstream distribution board. So if we check 100 amp MCCB upstream, 32 amp MCCB downstream from manufacturer's data, as is shown in yellow, what does that tell us? 9.3 kA. So that tells us we can achieve partial selectivity up to a fault of 9.3 kA. Now, hang on, bear in mind, the fault value at the downstream distribution board is only 8 kA. So there will never be a fault downstream from that distribution board or where the MCBs are of 9.3 kA. So although only the table tells us its partial selectivity is achieved up to 9.3 kA, that's not telling us the true story. Because the fault value is only 8 kA, we will actually be achieving total selectivity in this practical example. Okay, I think I'm going to hand over to you now to Richard.
I get to talk
about residual current device selectivity.
Yeah, but before we go forward, I'd like to thank Ian and Paul for that. That was a phenomenal display of selectivity, and now we discriminate between different overcurrent protective devices. It's still just as important when we look at RCDs. So regulation 536414 says that we should have selectivity in RCDs when it's required. As Paul's already said, it's not a requirement, it's a recommendation. But where we have to do it, we've got two ways of doing it. We can look at the upstream device being suitably time delayed, or the upstream device being within a ratio of 3 to 1. So if we look at RCD 21 there, we say that's a 30 milliamp device. RCD1 would need to be at least 90. We can't get 90 unless Ian and Paul want to make us one, which I'm sure they would. So we'd need a 100 amp device or an S-type device. That's great in a more simplistic, less complicated type of installation. We can do that quite easily, and we can see from here we've got a 30 milliamp device, 100 milliamp S-type up front, giving us some selectivity. We should be okay with that, shouldn't pose any problems. It's the kind of setup you'll see if you were, for argument's sake, looking to ensure that a fridge freezer didn't let go if it was upstream and you got a downstream RCD. So no problem there. So moving on, if we want to put an RCD in front of those two, we've got one or two options, but essentially we're going to be looking at devices that are going to bring in some kind of adjustability, either by the time it takes for the device to let go or the magnitude of the residual operating current. Really very complex piece of equipment, and we're going to bring the guys back again in a minute, but on an EICR, please bear in mind that those have already probably been set for a particular reason, and it's not a good idea to be going and tweaking them unless you've essentially found out before you tweak them what they should be. So when you're doing EICRs, just remember that you've got to almost try and get your head around these designs in case you come up against any of this kind of equipment we're going to talk about next, because you will have to code it and you will have to maybe tweak it for the owner if someone set them incorrectly. So please, Paul. So we've now got our complex installation, quite possibly a commercial or industrial scenario. We've got a 30 milliamp RCD feeding some final circuits, 100 milliamp S-type giving some selectivity there. And now we've got one more step, our adjustable device, and then another device again, where we require RCD protection of a type on some of those cables. They may be going through a particular area, they may be contained in a particular way. But those two devices there are very, very specific, and we have to make sure that they talk to each other and see each other correctly. So if I hand back to Paul from Hager, and he'll explain the reasons why we have to be very careful with those two devices and why we set them the way we do.
Yeah, thanks, Richard. So yeah, you'd have seen essentially two dials on most of these devices. One that allows us to adjust the milliamp rating as such, or the residual current rating, and one that allows us to adjust time. So you can see the top dial there, 0.03, 30 milliamps. And this particular device, of course, they're not all the same, of course, by the way. The different manufacturers may have different set points. But you can see the top device is adjusting the I delta N, the residual current setting, from 30 milliamps we've got setting on this all the way up to 6 amps in various notches in between. And you can see that the lower dial is delta T, or time. Now this is time delay. It's not the operating time, it's the kind of delay time. So you can see it has an instantaneous setting. The I is just missing off that picture there, INST. And then it goes 0.06, 0.15, etc. So that would be the actual delay time before this device would even think about starting then to operate. So back to the other slide, if we can think about the same kind of set of rules, if you like, where we try to meet the rule one is 3 times the milliamp setting. So on the top of the slide there, you see 300 milliamps is 3 times the 100 milliamp. So that's easy. Now, the thing we're not too sure of actually is what to set the delta T at of that device. Now, it says 0.5 of a second. Why does it say 0.5 of a second? Because the maximum operating time of an S-type device is actually 0.5 of a second. This is given to us in a table in Appendix 3, it's on the slide there. So you can see the delay S-type device, they will operate somewhere between 130 milliseconds. Okay, that's not min, that's not minutes, that's 130 minimum milliseconds, and 500 milliseconds is the maximum operating time. So that's the reason why we can have this setting, or we would suggest make the setting of the next RCCB in series from the picture there 0.5 of a second. So that's its delay time. So after that 0.5 seconds has expired, then it will start to work itself and activate. But the S-type is already tripped below 0.5 of a second. So that's the way we would kind of look at that setting. Now, the next one up, of course, we need to provide the same rules. So 3 times a milliamp. So if it has a 900 milliamp setting, we could set it to 900 milliamps. It probably won't, but it probably will have a 1 amp setting. Okay, so there's we achieved the 3 to 1. Now, we also need to achieve the delta T, or the delay time of the device in the question mark there, must be bigger than the total operating time of the next device downstream. Now, that's not 0.5 of a second, if you remember. 0.5 of a second is its delay time. It was then going to have an operating time after that. And then you'll have to consult the manufacturer there, of course. So the operating time of that device in the center of the screen there is probably something about 0.3 of a second. So it's got a delay time of 0.5 of a second, and then total operating time 0.3 of a second after that 0.5 of a second. So the actual total clearing time is probably 0.8 of a second. So the one with the question mark there, if we set that to 1 amp, 1 second, we will achieve a good level 4 level RCD selectivity by both using both time and current there.
That's brilliant, Paul. Just a quick question for you. We're getting towards the end, but whilst we're talking about that, if you're really struggling to achieve selectivity, we could have some other options, couldn't we? How we could minimise the fault happening in the first place. What would you say to that?
Yeah, I'm asked this quite a lot by customers where they really do struggle to achieve selectivity. Now, you can obviously then think about maybe reducing your risk of fault. So if in one of those examples we said the circuit breaker upstream, the circuit breaker downstream doesn't achieve selectivity to quite the level we want, so maybe we can use a cable method from the downstream device that reduces the likelihood of that circuit getting a fault. We could use armored cable or things like that. So we reduce its likelihood of fault in any case.
Okay, thanks, Paul. So all points back to at that design stage. If we want to achieve selectivity, we need to go through all these steps you've discussed. If we're struggling to achieve it, we may choose a different cable route, a cable method to minimise the fault happening in the first place. I think that's quite an easy concept to grasp. Okay, well, we're getting to the end here now, everybody. So just a quick reminder that we do offer design training as part of our NAPIT training offerings. Please have a little look on the site there on the screen if you're interested. Also, the guys over there at Hager, and I'll just echo what Richard said, fantastic, well explained, really good presentation. If you need any of that sort of training and you're wanting to use Hager devices in your design, then please get in touch with the team over there at Hager and they'll be happy to give you that expertise. Also, some of this design stuff, especially the energy let through, talking about how it affects cables, is covered in the on-site solutions, and we've got the suite of documents there if anybody needs any further guidance on testing and inspection and coding, etc.